Okay. Great. For a short lecture today, because I have a lot of stuff to give you guys back. We'll finish off 1.6 with the remaining examples that we didn't do, and then we'll actually do section 2.1. We just need one thing from 2.1, so that's going to be very short. And then we'll go. I'll give you guys stuff back. Review for the test will be up tomorrow on the same website where you find the quizzes and stuff. And so just remember that our test is on the 13th, which I believe is Tuesday. So this is 1.6 continued. Let's have a couple examples to finish off here. I believe we need to do this one. Because we did that e to the ln x squared minus 5 ln y, right? Yeah. We did that one. Okay, so I don't think we did this one. ln of the radical of x squared minus 1 over x times x plus 2 squared. Okay. Yeah, there was a problem similar to that in the bonus, well, in the quiz actually. And in the bonus, put a couple of those. And then we had to solve some equations. 1x equals 7, e to the 2x minus 7 is 10, 3 equals 5, e to the 3x, and 2 to the x squared plus 1 equals 5. Okay. And by simplifying this one, I meant to expand. Right, so we actually worked on a logarithm before where we actually combined a bunch of logs. This time I gave you one log, I wanted to expand it into several logs. The reason being both of these skills are very important. When you're expanding logs, it'll be easier to do calculus. If you're solving an equation, it's easier when you have one log. Okay, so if you're given several logs and actually to solve an equation where there's all these logs all over the place, it's to your benefit to actually combine all these logs into one and solve that equation. Okay, but if I give you a function where there's one big massive log and actually to do calculus like differentiate or integrate it, which we'll talk about, it's much easier to do that if you expand it. Right, so you'll both need to be able to contract logs and expand logs. So in this one, I want you to expand it using the laws of logarithms that we have. Ideas. What are you doing? All this is inside the log. Yeah?
Put it in like two different logs with a minus sign.
How would that work?
Like ln root x squared minus 1 and then minus ln x and then the log.
So we can do ln of this guy minus ln of that guy. And this is using the rule we have to do. Here we're using the fact that ln of a divided by b is ln of a minus ln of b, where the a is this huge mess up here, the b is the denominator down here, and we can split it up that way. What else could we do? Yeah?
Continue expanding. So ln radical x squared minus 1 minus ln x plus ln x plus 2 squared.
ln x plus ln of x plus 2 squared.
And then you can take out the exponents and put them to the front.
But is that okay so far? No, what's the problem? What are you shaking here?
There's a negative sign.
There's a negative sign, so?
Like, it should be
Parentheses, new parentheses here. That's going to be very important. So this negative sign will distribute to that one and make that negative. Okay? I'd also take this opportunity to actually write the radical as a power. Right? Because the very next thing Lewis said, to bring the powers down. Okay? So here we're applying that rule of addition with logs, where I know ln of something times something else is is equal to ln of this plus ln of that. Right? So this was a multiplication here, so I can apply that law. Now we can bring this power down. This is half ln of x squared minus 1. Here I have minus ln x, minus because it's distributed. Here I will bring the 2 down to ln of x plus 1. And here, of course, we're using the rule ln of anything to a power is just the power times ln. Anything else we can do? To get even simpler? Anything you see, anything jumps out at you? Because we can get simpler. Yeah? Yeah, so this is the difference of squares. You can actually factor this and actually break it even smaller. Right? X squared minus 1 is actually x minus 1 times x plus 1. In my other class, I put a 1 here and things actually combine further, but it doesn't matter. Okay, so, and then we can split this up using the addition rule again. And again, this happened in parentheses, so this half in front distributed to both of them. And so we can stop there. There's nothing else. And so now we have a lot more things to deal with, but for calculus, it's more convenient to have this form instead of that form. If you're solving an equation, it's more convenient to have that form instead of this form. So it depends on the goal. You'll know whether you want to combine logs or you want to expand the logs. Okay, so now we're going to do this one. Ideas, how do you solve it? Yeah?
You could just multiply by e on both sides.
Well, it's not
E.
multiplying by e.
Sure.
You want to use the rule where e to the ln of something is just a thing. That's what you want to use, right? So it has to be in the power. So technically, these two things are equal, so you can put them both in the power of e. Right? So you can do e to this equals e to that. You do it to both sides. You just put them both in the power. Right? If they're equal, then if I raise e to the either one, you should get the same answer. And so in the first case, our rule says the e and the ln cancel like this. You know, that's technically the wrong term. And so that will just leave you the next equals e to the 7. So you can actually use that rule. I don't remember what rule that was, but it's like rule 8 or 9 from what we said. You could also, by the way, use rule 1. There's the first rule that says you have log to the base a of b equals c. That means you can take a raised to the c and get b. In the same way here, if we had ln of x equals 7, you can think of this as log to the base e of this equals 7. So I can take e raised to the power of that and I get this. So either way you think about it, this is by far the more common way to think about it, using e's to cancel ln's. And you can also use ln's to cancel e's, of course, using the other one of these rules. Okay, so what do we do here?
ln time equals 2x minus 7.
So similar here, if both sides are equal, we can plug them both into the ln. They should give us the same answer. In the first one, ln of e cancels. I get 2x minus 7. Here I just have ln of t. And so now I want to solve for x. It's just like any other equation. Get everything that doesn't have x on the other side. And then divide both sides by 2. And that is it. Okay, what about this one? 3 equals 5e to 3x.
Divide by 5.
Huh?
Divide by 5. Yes.
Divide by 5. Okay, so we have 3 over 5 is equal to e to the 3x.
And then plug in ln.
Then you can ln both sides. This means that ln of 3 over 5 is equal to ln e to 3x. This means that ln of 3 over 5 is equal to those 2 x. This means that x would be equal to ln of 3 over 5 over 3. And of course, you can't actually cancel these 3's or anything like that, right? Because the 3 over 5 here is stuck inside of an ln. This 3 outside here is not. You can't infiltrate inside an ln like algebra. That's it. I think we spoke about this last time about how applying the rules as written is very important. So a common mistake would be to just ln both sides at this point, like you would here, which technically you could still work it out that way if you're careful, but you really don't want something between the e and the ln for that rule to apply, right? So a lot of students might have a knee-jerk reaction to do something like this. But you should know that you can't just cancel this with that, right? That wouldn't work because the 5 is here. Okay, it doesn't match up with the rule. You can actually split the ln in 2 parts. And then cancel here, that would be fine. Then move this over there. And you could still use the log rules to rewrite it as that. But I just want you to realize that if you ln both sides at this point, you can't just cancel and not worry about it. You couldn't cancel this and that and get 15x. So that wouldn't be correct. It's a common mistake. So if you want to do something like e both sides or ln both sides, make sure the e or the ln is by itself. There are no coefficients or anything else in the way. So the nicer thing to do would just be to get rid of that 5 in the first place. Then you can ln both sides. Ideas for this one? Yeah.
The log of 2, 5 equals x squared plus 1.
You said log base 2.
Yeah, 5. Of 5.
Of 5.
Yeah.
Oh, you're doing this side? Okay. Let's actually just log both sides first. So in this one, 2 is the base, so probably the best log to use is log base 2. Unless there's some other reason why you wouldn't want to use it. You could use technically any log, but log base 2 would be the most efficient here. Because according to our rules, that would cancel. This would give us x squared plus 1. Over here, we have log to the base 2 of 5. Whatever the power is, you have to raise 2 to in order to get 5. So your x squared would be log to the base 2 of 5 minus 1. And so your x will be plus or minus the square root of log to the base 2 of 5 minus 1. Now for a moment you have to worry about whether what's under the square root is positive, but we already know it's positive because log to the base 2 of 5 has to be bigger than 2, correct? Because log to the base 2 of 4 is 2. And so you'll need to raise 2 to a larger number than 2 in order to get 5. So this minus 1 is going to be a positive number, and so the radical is defined, and so that will be our answer. Okay. If for some reason underneath the radical was negative, you'd have to write no solution. It doesn't have to. Any questions on this? So that actually ends chapter 1. Tomorrow, for class tomorrow, we'll actually start on chapter 2. And in chapter 2, we're going to actually start calculus. So section 2.1 is not calculus, but we're going to hit 2.2 by tomorrow. And that's where calculus is going to begin. So it's a very exciting day. We'll end there, but I have a lot of stuff to give back to you. So you can sit tight for a bit.